the very first thing in this equation, so we can get it from here also. Replace each y by q dot, simply in this equation. Replace each y by q dot. So this is q k double dot plus gamma I j k q I dot q j dot. This is the acceleration of the curve, right? Any questions so far?
Yeah, I have a question.
Sure.
So this definition, how does it resemble the earlier definition that we made, which is the projection? So the first
It is exactly the same.
Yeah, the first two terms are the same terms, but the second term, which is the Christoffel, that involves the Christoffel symbols, should resemble the
That's right.
projection, right? But I can't see a direct connection between them.
Well, because the Christoffel symbols come from, it's as if there is a little bit of cheating here. Why? Because what are Christoffel symbols by definition? I should have a definition. This is the definition of the Christoffel symbols. What are these? It doesn't solve the problem. It says, please go and solve your problem for a frame that covers the tangent space. How are you going to do this? Well, you do it with projection and do everything, so it's already embedded in the problem. But we will see a way of getting this easier than doing it with projection, because doing it with projection is really cumbersome, right? We'll see another way, and this is the fundamental theorem of differential geometry. I don't think we'll do it today, next time we'll do it. But for me now, this is all what I care about, is that I found a way to compute the acceleration of a curve. This is, we can really go and compute it. I will give you gammas for now, and you can go and compute the acceleration of the curve. And in particular, we will have the definition of something very useful and very famous, the geodesic. What is the geodesic? It's just a straight line. And because we spend a lot of time discussing it in 241, I will not spend too much time with it, but obviously the geodesic, how do you define geodesic in this regard? Is a curve, what's the property? Yeah, it's a curve with zero acceleration. It's a curve with zero acceleration. So the curve that satisfies nabla gamma prime is zero. So it's a curve whose coordinate satisfies this second order differential equation. Okay? I love this equation because it's the heart of, lies in the heart of general relativity. We'll touch upon it next time. Let's have an example. So, S2 we have two coordinates. This is S2 is two-dimensional manifold, so this is x, y, and z. It's embedded in R3, but I don't care about the embedding now. I have two coordinates. Choose the coordinates you like. I will work here in spherical coordinates. So I have this guy, theta, and then we will go. This is a P on the sphere, so this is phi. So theta and phi, any P can be defined by theta and phi, right? At least locally. This means that I have two Christoffel symbols, two matrices, gamma for theta and gamma for phi, okay? How do you compute these guys? Well, go and do it from the rate of change of E theta with respect to E phi, E phi with respect to E theta, and all these combinations in the ambient space, project on the sphere to get these guys. It's really cumbersome. No, this is not the way we're going to do it in this course. But if someone magically gave to you, we'll proceed further, and next time we'll know a simpler way of computing them. So gamma theta here, I'm magically giving them to you until next time, so to show you how to get them easily. But at least we know a hard way of obtaining them. This is negative tan phi, and here is sine phi cosine phi 0, 0, 0. Okay? As you can see from the derivative here, please look at the derivative. This is very important because I will test you up on this. There are going to be homework giving you gammas, for example, and asking you to compute the derivative of x or of y with respect to x. Gamma completely determines the covariant derivative. Gamma completely determines this nabla kind of thing. If I give you gamma, you don't need anything else, correct? Do you see it from the definition, or do you have any question with that? So the Christoffel simples completely determine the covariant, the way we do differentiation. Okay, so using these gammas, I can define the derivative of anything. In particular, let's define the geodesic. What is the geodesic? It's nabla gamma prime should be 0. What's the equation? The equation is qk double dot plus gamma I j k qi dot qj dot is 0. So let's do it for k equals 1 or theta. So this is theta double dot plus this. I always interpret it as rho times your matrix times a column. Rho for the q dots, so this is theta dot phi dot, theta dot phi dot, and we are in the theta equation, so I put here gamma theta. So this is 0, negative 10 phi, negative 10 phi, and 0. So this is theta double dot minus 2 10 phi, theta dot phi dot is 0. This is the first equation of your geodesic, your straight line. And then we can do it for the second, which is phi double dot plus, again the same row, the same column, but here is a different matrix. This is gamma phi, which is sine, cosine, and 0 otherwise. So this gives you phi double dot plus sine, cosine, theta dot squared is 0. Two equations whose solution will give you theta as a function of time, phi as a function of time, right? So lumped together is a curve as a function of time. This curve is your straight line. Okay? Any question about that so far? Any questions?
Can we look at the entries of the matrix? For example, let's say gamma of theta. Right?
Yeah.
Gamma of theta. Can we say that the diagonal entries are, for example, the rate of change of E of theta and direction of E of theta? So this is the interpretation.
Oh yeah, exactly. Yeah. After projection. Yes, exactly. Yeah, this is the basic definition. Yes. Okay, I will go to a different animal. So I need you to take a deep breath. They are very related. We'll spend like the rest of the minutes with this, trying to relate, or at least to introduce this new animal and relate them next time. Any questions so far? The new animal is a bit simpler. The new entity is a bit simpler. It's actually, I'm talking about inner product. How to do inner product. Why we are interested in doing inner product? Because it's the best thing ever. If you can do it, you can do anything else. Inner product means we can measure angles between vectors. And if you can measure angles like we discussed before, you can measure length and you can measure distance. You can do norm and you can do metric. So the inner product, for us, we're going to define something analogous to do product on the manifold, which we call Riemannian metric. It's called the metric, although it's really a dot product. It's an inner product. Okay? How do we do dot product in Euclidean space? How we do it? We define a basis like E1, E2, and we do like EI with EJ is what? Anybody remembers? Very good. So, and because of linearity as well, you can do it the way you like. V and W is Vj, Wj, right? Because of linearity now, summation over J. Or actually, I can do it with respect to a matrix. Maybe I'm not fair to treat all the coordinates equally. Like here, what do you mean by Vj, Wj? I'm multiplying the x components, y components, z components. Maybe I favor the x components more, so whenever I multiply the x components, I'll multiply by 4. So I'm doing it with respect to a matrix A. So this will be Aij, Vi, Wj. Okay? obviously this matrix in order for this to be a dot product already, this has to be symmetric and positive definite matrix, okay? So this is, if you want to write it like the way I like, this is a row times the matrix A times the column W, okay? Indeed, in Euclidean space, you can do the inner product or the dot product like this, just with respect to a matrix, okay? Your matrix doesn't necessarily have to be identity. So it's as if we're saying dot product is just giving me a symmetric and positive definite matrix on your domain, nothing more. And this is indeed the Riemannian metric. The Riemannian metric is smooth map. It does it in a smooth way to preserve the manifold structure. It's a smooth map that takes, so say call it G. It takes a point and gives you a matrix, GB. G at this point, a matrix full of numbers. It's exactly like your A over there. It's symmetric and positive definite. Okay? As a map, it's bilinear in W and V. If W is multiplied by 4, it has to come out. V is multiplied by 2, it has to come out. So it's linear in these two guys, bilinear. So GP acting on 2 V and W, this is the exact same definitions, Gi, J, Vi, W, J, for all V and W in the tangent space TBA. That's it. So Riemannian metric is nothing but a symmetric constant definite metric. Is nothing but a way of doing dot product on the tangent space. Okay? Dot product on the tangent space. We do dot product between vectors, not between points. Over there, the notation is very confusing and sloppy. Here it's clear, we are on the tangent space. Okay. Whenever you have a way to compute dot product, which angles between vectors, it gives you a way to compute norm of a point, which means length, right? So given a curve in the Euclidean space, I'm still in the Euclidean space, just the things that you guys are very familiar with. I have a curve gamma. How to compute the length of that curve? Gamma is from A to B in time. Well, you integrate the norm of its velocity vector, right, dt. Well, but how to compute the norm? If I have dot product, I can compute the norm in terms of the dot product. That's simply the square root of gamma prime of itself, right? Any question about that? I will carry, because I have the same definition for, I have my own dot product, I will carry this over exactly the same. So L of my gamma on the manifold, it's exactly the same thing. Square root of my dot product. Dot product is written like this. Gamma prime with gamma prime, right? With the understanding that the computation-wise it's exactly the same. And this is G at gamma of t, dt. Any question about that? Any question?
Professor, is this map bijective?
Which map?
The metric?
The matrix takes two vectors and gives you a real number.
No. I mean bijective with respect to the point, for example. So the map, it takes a point and gives
a matrix.
Symmetric matrix. So I mean this map, is it bijective?
Bijective is surjective and injective, right?
Yes. I mean, if I give you a matrix, can I know which point at the manifold does this matrix represent the main product?
You know, the point on the manifold, I don't think so. I need to check, but I don't think so. Because we write it locally, we typically write it locally. So, yeah, you will suffer from the complete revolution kind of thing. I don't think so. Even in our usual examples, like sphere and spherical coordinates. So we can compute length of a curve. Okay, so now again, I'm interested in a metric. What do you mean by metric? To compute distance between points. So whenever you have a norm, you can compute a norm like this guy, you can define the distance or the metric. How? Well, the distance between P1 and P2 is simply here is the norm between P1 minus P2. Remember the hierarchy that I told you at the beginning of the course, that the inner product space is the highest And if you can do inner product, you can do norm. If you can do norm, you can do metric. Here is how we see it. Obviously, we cannot carry this definition over. Why? Because this is a ridiculous definition. We define the inner product for vectors, the norm for vector, and then you're asking me to apply it for points. Nonetheless, I need to subtract points, which we don't do here in differential geometry. We don't subtract or add points, right? We need to work with the inner product or the norm or the vector. But this is a good thing, because I can compute the length of any curve, right? So if you have 2 points, P1 and P2, obviously I can connect them with some curve, like gamma, or another curve, or a third curve, right? So I can construct gamma that takes 0, 1 to m, such that gamma of 0 is P1 and gamma of 1 is P2. I can do that very well. In particular, I can compute the length of the gamma, right? But these are too many things. Well, I will get the minimum. So I will construct this set and I will take its infimum. I will define this to be the distance between P1 and P2. Any question about that? Any question about that? You don't need to write after learning, you'll have this, but it's up to you. Any question about that? Okay, so we want to minimize L of gamma, which is the integral from 0 to 1 or a and b, it doesn't matter much, the square root of g acting on these guys, which is gi, j, q, I dot of t, q, j dot of t, dt, right? I want to minimize this guy. What type of problem is this? What type of problem is this? Minimize this L of gamma, subject to gamma at the initial point is P1, gamma at the final point is P2. So that is calculus of variations problem, right? This is your Lagrangian, go and do it. But actually it's better to, as always, when I have a square root, it's better to minimize the energy of the curve. I will remove the square root. Gij, which is function of q, qi dot, qj dot dt. This is your Lagrangian. Go and apply Euler-Lagrange to do your calculus of variations problem. Okay? And this curve that minimizes the distance between those 2 points, this curve, the result is what we're going to call, again, a geodesic. Because it's a straight line. A straight line, you can view it from 2 different perspectives. If I have a ruler, if I am in a space and I have a ruler that can measure the distance between any 2 points, then the straight line is the curve that connects the 2 points with the shortest distance. If I have a ruler. If I don't have a ruler and I have some other instrument that gives me how the rate of change of any vector along another vector, I can differentiate. I have a clock to tell me, okay, this changes fast, this changes slow. Then the straight line is defined as the curve with 0 acceleration, okay, if you can measure the acceleration. So here is geodesic straight line, which is the shortest distance. The curve that, the result, this is a hard problem. It's a calculus of variations, it's not always easy, right? Because I will solve this calculus of variations problem. The resulting gamma